we built a glove-controlled robot. It's one of a kind, nothing like it on the market. With the Kiwi Drive system, it's 3 omnidirectional wheels slapped together in a circle to move in any planar direction. And our custom glove, which takes tilt motions of the controller to move this robot in any direction. We believed if we constructed a course and presented this to high school students, their interest in engineering would be piqued, and perhaps they would go to university at U of T.
For background, the current Ontario high school curriculum offers very minimal facilitation of computer engineering and electrical engineering courses. In line with that problem, our motivation is to fill the gap between what's taught in high school and industry. And in addition to that, we polled students at high schools, and it showcased an 18% uptick in interest towards engineering and an 84% uptick in understanding of engineering and its career paths. So in short, our team successfully fabricated a demonstration module that meets all technical requirements, supersedes those requirements, and sparks an interest in pursuing engineering for high schoolers.
So our project is control algorithms for a planar electric motor, automated chessboards right now in the market. Use this design where they have one electromagnet inside the board that drags the pieces around. But this design isn't really optimal because it's slow, it's fragile, and the boards can get quite thick. So Evan came up with a new design that uses a 5-phase planar motor.
This motor is just the natural extension of a 3-phase motor, but the issue with them is that they only have a single degree of freedom, right? A 3-phase motor makes something spin around one axis, but to have a chessboard, you need to have something that moves in 2 separate dimensions at the same time. I'll make it do 2 loops. Hopefully it works.
Do you want to explain what this is about?
It's great. It's just a random test program that I came up with that just moves it around the board.
Okay.
Yeah.
Okay, so to talk a little bit about our project, we'll go through a quick little demo of the project. So basically, we have created a software tool to help clinicians rehabilitate patients who have suffered hand loss after suffering from a stroke or spinal cord injury. So the way that this is done is that they can upload a video taken off their, like a patient can upload a video taken off of a GoPro on their forehead, which would feature them interacting with objects on a day-to-day life. And a clinician can upload it to our platform. In our platform, you can upload a patient and you can upload a session, which would have the video in it. When you upload the video, it should run through all of the models. And if you click on the session, you should see all of the timestamps where you can see a user interacting with an object. So yeah, if you want to click through them, yeah, it'll seek to the part of the video in which they are interacting with the object. And in this way, a clinician can be able to see how a patient interacts with objects with their hand that is lost complete hand function, to be able to assess their treatment and rehabilitate them further.
One of the main issues we're kind of tackling with this is that when like a person gets like an injury and the clinician wants to kind of start beginning therapy with them, the time spent during like actual in-person therapy sessions is usually not enough. So they end up filming at home like 1 hour to 3 hour long videos. And so through the models and the UI, they're allowed to quickly scan through that video and get valuable information.
We were able to see people using the application and test it with actual user interface testing. So we were able to genuinely like watch people interact with their platform and see valuable results. And hopefully if this makes it further, or like if the research group ends up using it for other activities, it can actually help a lot of people.
Our project is called Airplay Instruments, and essentially what it is a gesture-based MIDI controller. So our project aims to use computer vision and machine learning to provide an alternative to physical MIDI controllers.
I'll just walk through the GUI that we've created for our project. First, I'm going to start with the chords instrument. As you see, when you click an instrument, it opens Logic Pro, which is the digital audio workstation that we're using. I'm going to click a chords-based instrument here, and I'm going to go back to my DAW. So that was a quick demo of like kind of the gist of our chords-based instrument. We have a couple other instruments we like to showcase as well. I'll cover our percussion instrument.
Yeah, so what we're doing here, essentially, we're tracking the thumb to decide which instrument to activate when it hits certain areas on the screen.
We can see that this MIDI data has actually been saved into the DAW, so it'll play back. That's just what I played.
So a major challenge with the adoption of electric vehicles today is the waste of second life EV batteries. Over the course of an electric vehicle's life, it can lose quite a bit of its capability, but that capability is still energy that can be harvested. So our project aims to take those second life EV batteries and repurpose them and use them as an uninterruptible power supply, primarily for servers.
We've rated from 1500 watts, which is the typical load case for a server. We have a centralized controller that manages the safety of the system and the battery, manages the connections that the battery has with the rest of the system and how it interfaces with the load. We have a switch controller, which is responsible for measuring the load when there's a dropout or a grid failure. Then this is responsible for synchronizing and turning off our system in order to supply the load without any dropout. So, and what that would look like physically here is this LED lamp would never turn off in the event of a grid dropout. This here is our central module controller that's responsible for, like I mentioned, all of the states of the system, and on it we have a charger that's responsible to its own high power converter, just under a kilowatt, that's responsible for charging the battery back up.
And just a few hours ago, we were able to get good results in terms of drawing power from our system and being able to switch quickly.
Today we'll be presenting our NLP drone, which is the natural language processing drone. So currently the solutions that are in place right now are basically like ChatGPT wrappers, as in that they're very basic. If I tell the drone to move forward, it'll do it. If I tell it to move back, it'll do it. But we want it to be more creative. We wanted to push the limits of what we can do through natural language. So what our drone is capable of doing is basically follow natural language commands such as move forward 5 meters, or you see that yellow chair there, move towards that yellow chair. It should be able to distinguish between a yellow chair and a blue, black, red chair. And that is all implemented through our systems that we have in place here.
We actually recorded many demos and we'll show the most relevant ones.
The first one is abstract decision making. So this is more conceptual stuff like, can you draw a T in the sky? Can you maybe do a circle? In this example, it's going to be, can you draw a square in the sky? And this is a more complex command, so it might take a moment for the large language model to process it and output something. Right. So that's it, drawing a large square. Now here is object identification and detection. In this video, it's going to be asked to go to that table and then land on it. And the very first thing it does is look around for the actual table. The camera is actually facing towards us right now, so it's going to keep turning until it finds the table. And of course, it's also able to identify the exact location of the table as well. And then once it gets all that information, it returns to its original position and then executes these commands. Right, so that is how it's able to interact with this object.
Our project is Aspire, which is an AI mock interview tool. Current mock interview tools don't assess feedback on interview answers based on STAR and nonverbal cues and verbal speech. So there's no tool that's out there that kind of combines everything together.
We have our project open here on this laptop. This is where users can go in and start a session. Once they start a session, they can select from one of 6 different categories. I'm going to go with teamwork. And once the user selects a category, they can select the number of questions they want in their mock interview session. I'll just go with 1 for now. And now you can see that our session has started. The question is prompted and the user is given some time to prepare their answer. The question is, tell me about a time when you had to work closely with a team to achieve a challenging goal, for which a sample answer could be, one time that I had to work closely with a team to achieve a challenging goal was when I had to work in a group of 4 to build a complex project for a capstone. And now I can stop recording, and now the system will analyze our response. So that can take a bit of a while because there are 3 models here. Yeah, so this is how the feedback looks like. We start off with the transcript of what the user said. This is using Azure speech to text. We have some overall feedback provided by a large language model. And then for our performance tab, we have our scores on various different subjective, non-verbal interview metrics. And finally, we have our STAR model, which detects situation, task, action, result from the transcript mentioned earlier.
Hi everyone, we're AI Fashion Mirror Group 3.
To do a quick demo here. So once we click to start, our software will take a photo of you, and then it will send to ChatGPT, extract the user features of what you're wearing, and then generate what it thinks would look good on you, and then it will query from our database. Let it load for a second. Oh, as you can see here, you feel free to swipe through the results. So it's looking at these products, and then also the comments below. It's the feedback and comments of the reasons why it thinks this product would look good on you.
Today we present to you our project, which is a functional near-infrared spectroscopy brain device. So essentially, the background of our design is based off of a theory called near-infrared light to measure brain activity, specifically the changes in brain oxygen levels. So this is useful for clinical settings, for research settings, and for educational purposes. So I'll pass it off to Tony to talk about the hardware.
So we designed our own device, everything from hardware, software, firmware, mechanical. Here you can kind of see the board is what we designed. So it has functionalities of using emitters and detectors used to measure different wavelengths and concentration levels in your brain. So we designed our sensors to have different wavelengths of emitters as well as detectors. And then we have our ECU unit, which is our electrical control unit, to basically process all this data and then transmit it to USB. And then we have a GUI as well that you can kind of see.
In terms of the software design, we've implemented an interactive GUI for the user to be able to visualize ADC data in real time, as well as controls for the user to be able to control the firmware from this interactive user interface. And in addition to supporting live ADC readings, we also have options for the user to record data and cover useful metrics such as oxygenation and deoxygenation levels in the blood.
So I'm very pleased to introduce our project. It's called AReducate. So a lot of students really struggle with programming concepts because it's very abstract. And an easy way and a proven way to help those abstract concepts become tangible is by using visual tools. And one that's very proven is AR.
So our platform involves two different parts. One is the actual editor, which the professors can use to create AR modules really quickly. What we tried to do was really strip it down to the bare bones of what an editor can do. Just add objects, create animations, and quickly share it with your students. Once the students get the link, they can just open it on their phone, on their browser of choice, and point it at a marker and be able to see that module immediately.
Okay, so now we can go into a quick demonstration of our platform. So this is our platform, AReducate. Here, I'm basically going into the objects library and selecting from a list of assets. So here I put in a box as well as a sphere. Now I can go into the asset customization tab. So here I'm changing the name of the asset as well as the label, changing the color, and then I can go on and modify things like its position, its rotation, and scale, which is what I'm doing here. And then after you customize your asset, we can go on to animate it, which is done through the bottom part, which is the animation editor. And now I'm gonna just quickly play it to show it to you how it looks on the editor. Yep. And then afterwards, I can go on and preview it in VR just to see if it looks as expected and make any quick changes if I need to back in the editor. If it does, I can then generate a link to the AR environment and then paste that link into a new tab. And this link is shareable, so anyone can use and access this link to see that AR preview. And then it looks as expected, which is what I just created in front of you.
And we'll show you a quick demo on what the student interface would look like. So after scanning one of the QR codes, I'll get a pop-up that says allow access to camera. And when I do that, I point it at the hero marker, and you can see that I can move it with my gestures, and every time that you want to restart the animation.
So you can visualize the entire tree from every angle.